So let's dive right in. We're starting today, really in the thick of it, looking at New Delhi. Just recently, October 2025, the government tried this pretty high-stakes cloud seeding trial.
Yeah, talk about pressure. Trying to literally wash the smog away when the AQI is, what, over 300?
Exactly. A very temporary and honestly quick, costly move.
It really highlights where this technology is at, doesn't it? I mean, cloud seeding. It's not just about helping farmers with drought anymore.
No, it seems like it's become this emergency tool now, touching on public health, definitely water rights, and even, well, international tension.
For sure. So today, we really need to unpack this. Is cloud seeding this, miracle cure with huge economic benefits?
Or is it more like an expensive Band-Aid, maybe hiding bigger problems? We need to look at the science, follow the money where it seems to work.
Right, like in North Dakota.
Yeah, exactly. But also tackle the doubts, the safety questions people have.
And critically, the geopolitics.
Hmm.
This idea of weather control, it's not science fiction anymore. It's happening.
Okay, so let's start with the basics for you, the listener. What exactly is cloud seeding?
Well, at its core, it's a weather modification technique. The whole goal is just to enhance precipitation, get more rain or maybe snow out of a cloud than you get naturally.
Right, enhance. That's the key word, isn't it? You're not creating clouds out of thin air.
Absolutely not. You can't just, spray something into a clear blue sky and make it rain. You need an existing cloud, and it needs to be, well, suitable, rich in moisture.
Suitable. So, like, ripe for seeding. What does that mean practically?
It means two main things. First, enough moisture. Often you need humidity levels over 50%, sometimes even higher.
Okay.
And second, the temperature inside the cloud is critical because the method, the agent we use, changes completely depending if it's a cold cloud or a warm cloud.
All right, so let's say we have the right cloud. How do we actually seed it? What are we putting up there?
We generally use two types of agents. For cold clouds, these are the ones with supercooled water droplets. Think temperatures between -20 and maybe -7 Celsius.
So below freezing, but the water hasn't turned to ice yet.
Exactly. For those, we use what's called glaciogenic seeding. The common agents are silver iodide, AgI, or sometimes dry ice, which is just frozen carbon dioxide.
And how do they work?
They act as ice nuclei. Their structure is very similar to natural ice crystals. So they basically trick these supercooled droplets into freezing onto them. They grow quickly, become heavy, and fall.
Silver iodide. That acts as the trigger point, the little seed crystal.
Precisely. It provides that necessary structure. Now, if you're dealing with warm clouds, so
Yeah.
temperatures above freezing,
Right.
you switch gears to hygroscopic seeding. This usually involves dispersing really fine particles of sodium chloride.
Just table salt. Seriously.
Pretty much, yeah. Simple table salt. Salt is hygroscopic, meaning it attracts water vapor really well. So these salt particles help the tiny cloud droplets collide and grow into much larger drops, big enough to fall as rain.
Okay, that makes sense. So how do we get this stuff, silver iodide, salt, up into the clouds? I picture planes mostly.
Aircraft are definitely a major method. They can fly directly into or above the cloud, releasing the agents from flares attached to the wings,
Mm.
or sometimes dropping pellets of dry ice, very targeted.
Mm.
But you also have ground-based generators. These are common, especially over large agricultural areas like the U.S. plains. They basically burn a solution containing silver iodide, and the smoke, the plume, gets carried up into the clouds by natural wind currents, the updrafts.
Ah, so less precise relies on the wind cooperating.
Right, definitely wind dependent. And then you have some, let's say, more assertive methods. China, for instance, uses rockets and even artillery shells packed with seeding agents pretty extensively, especially over vast areas like Tibet.
Rockets and artillery, wow.
Yeah, and the UAE has been experimenting with drones. They use drones to deliver an electrical charge into clouds, which can also encourage droplets to merge, interestingly, without using any chemical agents at all.
Electric charges. Oh, that's novel. So that covers the science basics. But the conversation really shifts when we look at the economics, doesn't it? Because effectiveness might be debated in some circles, but in places like North Dakota, this seems like big business.
Oh, absolutely. North Dakota is the classic case study.
Hmm.
The North Dakota Cloud Modification Project, the NDCMP, it's been running a long time. And they have some of the most solid data showing, real sustained economic benefits from seeding, primarily for agriculture protecting crops and boosting water supply.
So what does that data actually show? What are the long-term results they're seeing?
Well, the independent evaluations consistently point to two key outcomes. First, they demonstrably increase summer rainfall in the target areas by about 5 to 10%.
Okay, 5 to 10% more rain. That's significant for farmers.
It is, but maybe even more impactful for their bottom line is the second finding. They've reduced crop damage from hail by an average of 45%.
45%, that's huge. Hail can wipe out entire fields. But hang on, running these programs must cost something, right? Planes, pilots, the seeding materials. Does the cost eat up the savings?
That's always the critical question. And according to the analysis, especially one from around 2009, the answer is a pretty emphatic no. The dollar values are actually quite striking.
Okay, lay it on us.
So the direct value just from the increased crop production, that extra 5 to 10% rain, was estimated between $8.4 million and $16 million annually.
Wow, okay, just from the extra yield.
Right. Then you add the savings from not losing crops to hail, which averaged about $3.7 million per year.
So total direct impact is what, roughly $12 million to almost $20 million a year?
Exactly. Now here's the kicker, the real aha moment you mentioned.
What was the program cost?
Back in 2009, the projected annual cost for the NDCMP was about $768,000.
Okay, so wait, you're spending less than $1 million to get back potentially $20 million.
Do the math. The benefit-to-cost ratio is, well, impressive. It's 16 to 1, even if you only assume the lower 5% rainfall increase. If they hit the 10% increase mark, that ratio jumps to an incredible 26 to 1.
$26 back for every dollar spent. That's almost unbelievable for any kind of environmental or agricultural program. It makes rain practically a tradable commodity with a massive return.
It really reframes it, doesn't it? And remember, that's just the direct impact on farming.
Ah, there are knock-on effects, too.
Of course. When you factor in the total gross business volume, all the secondary economic activity that ripples through the local economy because the farms are doing better, the annual benefit was estimated somewhere between $37 million and over $60 million.
Okay, so when the conditions are right and it's managed properly, cloud seeding isn't just wishful thinking. It can be a serious local economic powerhouse.
Precisely. A very powerful tool in the right context.
Which brings us back to that tension. If the ROI is 26 to 1 in North Dakota, why is there still so much scientific debate globally about whether this stuff actually works consistently?
Yeah, that's the crux of it. The skepticism mostly comes down to the inherent messiness and variability of weather itself. It's just naturally chaotic.
Right.
So groups like the U.S. National Research Council pointed out back in 2003, it's really hard to definitively prove, statistically, that seeding is causing a huge effect in every single case. Natural rainfall varies so much anyway.
So separating the signal from the noise is tough. You make it rain, but proving it wouldn't have rained that much anyway is the challenge.
That's a statistical headache, yeah.
Yeah.
But that said, the evidence for positive results has been accumulating, especially in specific conditions.
Like where?
Well, the American Meteorological Society acknowledged back in the late 90s that seeding supercooled orographic clouds, that's the clouds pushed up over mountains, has been shown to increase seasonal precipitation by about 10%. It's pretty consistent.
Okay, so mountain ranges are a key factor.
Often, yes. And more recently, look at India's KIPX study around 2018-2019. They found in specific rain shadow areas they could boost rainfall by an average of 18%, sometimes up to 46% in certain locations.
Wow, 46%.
Yeah, under the right conditions, particularly when there's already plenty of moisture moving through. It shows that locally, under optimal circumstances, it can be very effective.
So highly dependent on the specific geography and atmospheric conditions. Not a silver bullet everywhere. Okay, let's tackle the other big concern people raise. Safety. Spraying chemicals, specifically silver iodide, into the sky. People worry about toxicity. Is that a valid concern?
It's a very understandable concern. You hear silver, you think heavy metal. But the chemistry here is really important. Silver iodide, AgI, is actually practically insoluble in water.
Insoluble. Why does that matter so much?
Because it means the silver doesn't really dissolve and spread widely in the environment in a harmful form. Instead, the traces of silver that do come down tend to quickly bind with sulfur in the soil and water, forming silver sulfide, Ag2S.
Silver sulfide. What's that?
It's essentially inert and non-toxic. It's the same compound that makes your silverware tarnish. It just settles out and becomes part of the background environment without causing harm.
Okay, so it gets locked up quickly. What about the actual concentrations found in the rain itself? Is it safe to drink?
The levels are extremely low. Studies typically find maximum silver concentrations in seeded rainfall around, say, 20 micrograms per cubic decimeter. That's per liter, basically.
20 micrograms per liter. How does that compare to, like, standard drinking water regulations?
It's well below the limits. The U.S. EPA standard for silver in drinking water, for example, is 50 micrograms per liter. So we're talking about levels less than half the accepted safety threshold.
Right.
And the other part, the iodide. It's a stable, non-radioactive isotope iodine-127, which is actually an essential nutrient for human thyroid function.
So the scientific consensus is negligible risk.
Based on everything we know currently, yes.
Yeah.
Decades of use and study haven't shown any immediate conceivable danger to public health or the environment from AGI seeding as it's currently practiced.
Okay, that's reassuring on the safety front. So let's circle back to these high-stakes uses. North Dakota is about boosting crops economics, but Delhi, that was using seeding as an emergency fix for air pollution. Is that a sensible application? Or is it, like some critics say, using a scalpel for a cannonball wound?
That's exactly the critique from many atmospheric scientists.
Yeah.
Delhi's recent attempts, that $3.201 Coast Core initiative for just 5 trials, it was really aimed at perception management, trying to get a temporary cleansing effect by forcing rain to wash particulates out of the air.
But didn't they have trouble even getting it to work before?
They often do. There are huge technical challenges. For one, seeding often requires decent moisture levels, and heavily polluted air masses can sometimes be relatively dry below that minimum threshold needed.
Ah, so the pollution itself might hinder the solution.
Ironically, yes. And even when they do manage to induce some rain, the effect is incredibly short-lived. Experts call it a costly Band-Aid. The rain might clear the air for a few hours, maybe a day or two if they're lucky.
But the pollution sources are still churning it out.
Exactly. The traffic, the industry, the agricultural burning, whatever the sources are, they haven't stopped. So the smog just bounces right back. It doesn't solve the underlying problem at all.
So scientists are pushing back, saying this diverts attention and resources from the real long-term solution, which has to be cutting emissions at the source.
Precisely. You can't just keep trying to hack the atmosphere with a tool that needs very specific conditions, many of which might be missing, to fix a massive chronic emissions crisis.
Okay, beyond the smog issue, there's the even bigger elephant in the room. Using weather modification strategically, even potentially as a weapon, that has a history, doesn't it?
It absolutely does. The most well-documented and frankly chilling example is Operation Popeye. That was the U.S. military during the Vietnam War from about 1967 to 72.
What did they do?
They ran a large-scale cloud seeding program over the Ho Chi Minh Trail. The goal was to extend the monsoon season, make it rain harder and longer to try and disrupt North Vietnamese logistics, turn the trail into mud.
Wow, they weaponized the rain itself.
They did. And it apparently had some success, extending the rainy season by 30, maybe 45 days in some areas. It proved the concept was viable.
And that led to international action.
Yes, that operation was a major catalyst for the 1977 Environmental Modification Convention, the ENMO-D Treaty, which specifically bans using weather modification for hostile military purposes.
Okay, so direct weaponization is banned, but the geopolitical risks haven't vanished, have they? They've just shifted.
They've shifted more towards resource competition, especially water. And the risks are amplified in certain sensitive regions. Think about the Himalayas.
Why there specifically?
Because China operates a huge cloud seeding program across the Tibetan Plateau, aiming to increase water availability for its own rivers. But Tibet is the source of major rivers flowing into South Asia, including India.
Right, and mountains affect rainfall.
Dramatically. That orographic lift air forced up the mountains naturally enhances precipitation. So China's seeding efforts upwind could, potentially unintentionally or even deliberately, cause significantly heavier monsoon rains downstream in Indian states like Uttarakhand or Himachal Pradesh.
Leading to potentially catastrophic floods far worse than usual, like the 2013 Uttarakhand disaster.
That's the fear, an unintended consequence, or maybe not entirely unintended, with massive cross-border implications. It's a huge potential flashpoint.
And it's not just about too much water, is it? There's the opposite problem, too.
Exactly. The downwind effect, or sometimes called rain shadowing. If you successfully seed clouds and make them precipitate heavily in one area, you might be effectively removing moisture that would have naturally traveled further downwind.
So you could cause or worsen droughts in neighboring regions, maybe 50 to 150 kilometers away.
Potentially, yes. Which leads to accusations of cloud theft or stealing rain. Iran, for example, has voiced concerns like this about neighboring countries' seeding programs possibly impacting their water supply. It's a very real source of tension.
But given all this, how reliable is cloud seeding really? Could it actually be used as a precise weapon today, despite the treaty?
The consensus seems to be that its reliability as a target weapon is still quite limited. Yes, you can influence the amount of rain locally under the right conditions, but you can't really steer the clouds themselves. You can't change the overall weather pattern or direct a storm precisely onto an enemy target. The large-scale atmospheric dynamics are just too powerful and chaotic.
So it's too unpredictable for tactical weapon use, probably.
Probably. It's more of a blunt instrument that carries significant risks of unintended consequences, both environmentally and politically.
Okay, so let's try and synthesize this for the listener. We've seen cloud seeding deliver that remarkable 26-to-1 ROI in North Dakota, a clear economic win in a stable agricultural setting.
Right, where the goal is specific and localized enhancement.
But then we see it used in Delhi for smog, where it's criticized as a temporary, costly, and largely ineffective fix for a systemic pollution crisis.
A tool misapplied, essentially.
And finally, we see the potential for cross-border conflict, whether it's floods in the Himalayas or droughts downwind, huge geopolitical risks stemming from trying to manage a shared, moving resource like atmospheric moisture.
It really boils down to this. Cloud seeding works, scientifically, under specific conditions for local enhancement. Has proven economic value there. But its limitations are stark when we try to scale it up to solve massive problems like pollution, or when we use it near sensitive borders. The science bumps up against the chaos of weather, and the politics bump up against sovereignty and resource rights.
Which leads to a final, really fascinating question that the source materials raise, something for you, the listener, to think about. It's a legal and almost philosophical puzzle. Clouds move, they drift across borders constantly. If one country seeds a cloud and makes rain fall over its territory, potentially taking moisture that might have fallen elsewhere, who actually owns that cloud? Who owns the water in the atmosphere?
Yeah, it's a profound question. International law really doesn't have a clear answer yet. How do you apply ideas of territory and ownership to something as fluid and transient as a cloud?
It forces us to rethink what sovereignty means in an age where we can actively manipulate the atmosphere itself. A question with no easy answers.